Hi guys, today we are going to discuss about current mirrors. What is a current mirror? A current mirror is a transistor circuit that replicates current from the main current source, or you can call it as an ideal current source. But first, why do we need a current mirror? A current mirror has a lot of advantages, but one of the main reasons or one of the main uses of a current mirror is setting up stable and a constant bias current for the active devices. If all we need is a bias current, we can generate this a constant bias current through by using a constant battery source or through a resistor divider. But we cannot use these components because there is an actual difficulty with physically using these components, and also one of the main reasons are they are temperature dependent and they are also dependent on VDD. So we need a device that produces a stable and constant bias current for our active devices in a way that they are not dependent on the temperature and also they are not dependent upon the global VDD. And current mirrors overcome these limitations. Let's see how they overcome these limitations. An important configuration that we'll be using in current mirror is a diode connected transistor. A diode connected transistor is a configuration where the gate terminal is connected to the drain terminal of a transistor. And an interesting feature about this configuration is the transistor always remains in saturation. A transistor is in saturation when the drain source voltage is the gate source voltage minus the threshold voltage. In case of a diode connected transistor, the gate and the drain are shorted together. So this forces the drain source voltage to be gate source voltage minus the threshold voltage. This is how a diode connected transistor always remains in saturation. Now I'm going to do a large signal voltage sweep to this diode connected transistor. So this is the diode connected transistor. The gate is shorted to the drain. So I'm going to connect a voltage source V1 across the drain and the source. And I'm going to see the how the current changes with the voltage. So this is M1 and this is the current that flows. So we know that M1 is in saturation, so ID is equal to 1 by 2 mu n C ox W by L1 VGS minus VTH the whole square. Here VGS is equal to VDS, which is equal to V1. Changing the equation accordingly, we get 1 by 2 mu n C ox W by L V1 minus VTH the whole square. This will give us a quadratic equation behavior. So let's see how this can be interpreted in a graph. Let me change the color. So V1 will be, when V1 is at 0 volts, I1 will also be 0 because the transistor is off. And it remains off until VDS is equal to VGS minus VTH. So this is the point where it happens. Once it passes this point, it performs according to the equation that we have derived here. So this is a quadratic equation, so the characteristic will be something like this. Now let's sweep a current source instead of an voltage source. So I'm going to connect a current source to the source and the drain terminal. This is diode connected and this is I1. We already know the equation of the current, which is 1 by 2 mu n C ox W by L V1 minus VTH, the whole square. It is as if we are trying to find the inverse of whatever we did in the voltage sweep. From this we can actually get the value of the equation for V1, which is 2 I1, the ID is I1, divided by mu n C ox W by L, it's the square root of this entire term, plus VTH. Having these two equations in our mind, let's try to see how this circuit will behave. So I'm going to take a diode connected transistor. Let me move this a little, to which there is a current source connected. And the output of this circuit is a voltage signal that I'm going to give it to the gate of another NMOS transistor. Let's call this M2 and this is M1. So we're going to find out what I out is and how I out and I1 are related. So the voltage that will be given is V1. Let's keep that in mind. So I out, assuming the transistor is in saturation, I out is equal to 1 by 2 mu n C ox W by L of transistor 2 V1 minus VTH, because VGS here, the VGS is equal to V1. We already know what V1 is, so I'm going to substitute that. I out is equal to 1 by 2 mu n C ox W by L of transistor 2 square root of 2 I1 divided by mu n C ox W by L of transistor 1 plus VTH minus VTH the whole square. There is a plus VTH here and there's a minus VTH here. So cancelling out all the terms, we get this cancels out and this is a square root, so cancelling out everything, we get W by L of transistor 2 divided by W by L of transistor 1 into I1. And this is how the current mirror calculation can be done. From this equation, we can see that the current source that is connected to transistor M2 is directly related by just the reference current, which is the I1, and it only depends on W by L and it does not depend, it is not temperature dependent, or like it is not dependent to the source. And this is the current mirror equation based on which we'll select the width and length of the transistor depending on what kind of ratio of currents you need, and this is for a very simple basic current mirror type. Thank you so much for watching and stay tuned for more videos. Bye.